Okay, so the title of my talk, there are two titles of my talk, Recursion, non-recursively, and Algebras and fixed points. This is my first Scala talk, by the way, so hi. Who am I? David Barri, hello. You can find me on GitHub and Twitter, those handles. I've been programming for 28 years, since I was a kid, and I've been doing Scala and FP for the last 4. I'm working on my own startup, which is around software requirements, and I'm using Scala for that. I also do a lot of open source. These are some of my libraries. You may have seen them. By the way, if anyone uses Scala.js React, 1.1.0, wait, speaking in front of people, I'm sorry. 1.0.0 RC1 came out today, so have a look at that. It's really cool stuff. Oh, thank you. Right, so functional programming. I've been doing this for 4 years only, and I absolutely love it. It's been a fantastic experience. It was hard to get into at first, I'll admit, but it's been worth it. The payoff has been unbelievable. So I used functional programming all over the place. It's very, very humbling. I just wanted to show you this, S to an SA. Does anyone know what that is?
State monad.
That's right, state monad. So state monads are built on just this very simple underlying function. A type S that goes to a tuple of S and an A. It's so simple, but you can build so much on top of this. And this absolutely blew my mind once I grokked it. Like, I really find this beautiful. The amount of stuff that you can do with that is amazing. In the same vein, today I'm going to talk about an FA to an A. That's one constituent of today's talk. When I grokked this, I found this like mind-blowingly beautiful. How much you can do with just this tiny little simple function. And a bunch of other stuff. But okay, just quickly, a show of hands. Who could implement a red-black tree right now? One. He's only putting his hand up because he knows someone asked him to do it. On the other hand, who knows how to use map and set? Right, pretty much everyone. Who finds them beneficial? Pretty much everyone, right? Right, I think there's an important observation there. Tonight, I'm going to talk about a lot of things, and depending on where you are in your journey with regard to programming, a lot of it could be overwhelming if you're new to a lot of the things I present here. And if you don't get it, if you don't understand how everything works or why it works, it's okay. Really, just trust that it does and know that you can do really cool things with it and just know how to apply it. Then in your own time, I think you can go at your own pace and delve into the how and the why a bit more. It's a really good way to get started. Okay, so this is an agenda of my talk, just so you know where we're going. Right, recursive data. So this pops up quite regularly. Let's talk about what it is and some examples. So these are some examples from Shipwreck. So in one part of requirements are use cases. And this is an example of a use case. It's just describing what a user would do and how whatever system they're using interacts with them. And you can see that it's recursive. You have 1.0 at the top, and then that has children like 1.0.1, 1.0.2. That has children. That's an example of recursion. This is a filter that you can type in. This is recursive too. They might not look it, but you have an expression, and then in the parenthesis you have a sub-expression, and you could have a sub-expression in that as well. So that's another example of recursion. Here, if you have a bunch of, let's say, strings, and they all have similar prefixes, you can use a prefix tree, or sometimes just try. Some people pronounce it as try. It comes from retrieval. And then you can actually model it as a tree like that, and it's much more efficient. What else? I have a self-referential many-to-many relationship data type, and within that you can actually just choose a node and then get a view of its children all the way down as a tree, or its parents all the way up as a tree. In one of my open source libraries, there's one called Nyai, which I'll show you a bit later, which is random data generation, property testing, state assertion. You can represent logic. That's recursive again. Parentheses are the key there. In test state, you can create actions and validations and properties and stuff like that, and compose them all, and that composition's recursive as well. So I didn't realize this before, but I have got a lot of recursive data in my code. Some more everyday recursive data types: linked lists, recursive; maps, sets, JSON's recursive; arrays and objects can have sub-JSON. So why is it useful? One reason is that it models reality. In reality, certain relationships can be recursive. So like you have friend book, and you have friends who have friends who have friends. If you have a file system, you have directories which have directories, blah, blah, blah. It's also useful for efficiency. You can use hash maps and binary search to save time. They're much more time efficient if you model them with recursion in certain ways. Same thing with space. If you've got a prefix tree or interval trees, discrete interval trees, that saves a lot of space by switching to a recursive structure. Okay, so for the next half of this talk, we're going to use a calculator example because that's sort of canonical when it comes to this kind of thing. This is a very, very simple. Oh, I forgot to mention, there are a bunch of Python people and .NET people in here today. All of this applies in any language. It's not Scala specific. So if you don't have the opportunity to use Scala at work, you can at least take these cool approaches and use them anyway. Okay, so here I'm modeling a calculator. I've only got three inhabitants of calc, which is one is a number, which is literal, and then a means of adding two numbers together and a means of multiplying numbers together. Now you'll see that in add and multiply, I've actually got calc in there as well. I didn't put int or I didn't put number. That's because I want to be able to have sub-expressions. And you can see an example of what that would look like down the bottom. See, sub-expression, and it just goes in brackets. Now there are a few problems with this. The first is that in an approach like this, you don't have any control over the recursion. It's hard-coded, it's always going to be recursive, and that recursion is always infinite. You have no abstraction over depth.
Recursion is the go-to functional programming.
Yeah, uncontrolled recursion. The second problem is it's often hard. I think you'll find that, I don't think anyone will disagree with the statement that it's much easier to write non-recursive code than it is to write some kind of recursive case. The third problem is you can't annotate nodes in a structure like I had. What do I mean by that? This is an example of node annotation. Say you've got a person, you're modeling a person, they've got a name, they've got an age, they've got a list of unsaved friends. Like I said, I haven't looked at this in a while. What was I doing? All right. Right, what we want to do is annotate all the people in this structure with an ID. So below is how we would do that. So we'd say, well, we'll create a new class to represent the ID of a person, and then we create a new structure which is person with ID as opposed to person. If you have a look at their friends, the friends are now a person with ID. Right, that and that were probably supposed to match. Okay. Sorry, and the point here is that I had to create a completely separate structure just because I wanted to annotate something. So there's no reuse, well, not much. Another example of annotation is, back to the calculator example, if instead of just calculating a result, you wanted to sort of trace how that result was calculated. And in this example, I'm doing that by adding a hard-coded log string that describes what it does. And again, changing the structure of calc. So every time we want to annotate something up until now, we've created a brand new structure. So how can we allow any kind of annotation to our calculator? Well, this is the naive kind of approach, something that you might try at first and then get sick of very fast. You can parameterize the annotation. Just say, I'm going to call the annotation A. Everyone has an annotation of A. What A means is arbitrary. And that works, but it's not very good. And is there a better way? Yes, there is. So what we do, instead of creating a type for the annotation, you create a type, you parameterize the recursive type. So if you have a look at the bottom in the after block, you'll see that add and multiply no longer refer to calc. They just refer to some arbitrary A. A has no bounds on it. It has no constraints that tie it to calc either. It could be anything. That's step one, generalize the recursive type. All right, and we're not done yet though, because if we go back to the calc example, you might just think, oh cool, I'll put a calc in there and it'll refer to itself. No, this won't compile. Why is that? Well, we have to talk about the difference between types and type constructors here. Type constructors are like functions. They're not actually types. You have to give them other types, and then the result of that is you have a final type. So you can't have a list or a map or a future in Scala. You can have int, strings, and units. If you want to turn list into a real type, you have to give it a real value. So you can have a list of ints, a list of strings, so on and so forth. So coming back to calc. Calc is actually a calc constructor, a type constructor, right? What can we put in there? Well, we can put unit, we can put a list of ints, we can put nothing, which means it's impossible to inhabit those types. This is where we get recursion from. We can go calc of nothing, which means you can have a depth of 2, calc of nothing, have a depth of 3, and so on and so forth. Still not very good, but it does work. So in these two examples, see, I've limited the depth to 3. You can have 0 to 3, 1 to 3, and that's it. Oh, 0 to 3, anyway. Right, fixed points, step 2. This is how we get infinite recursion. So have a look at this class. This is one of those things you don't really need to understand. I'll do my best to explain it. If you take that f that's given to a fix and expand what its value is, just by doing substitution, you end up with this. Substitute it once, you get that. Substitute it again, you get that. Substitute it again, you get that. And it just never ends. We could keep substituting all day long, and that's a little trick, I guess, to represent infinite recursion in terms of types. So instead of having a calc of something, what we do now is we have a fix of something, and the something in this case is calc. So we have a fix of calc. Fix means an infinite layer of calcs. That's another way of looking at it. And I mean, practically what you do is you annotate, you wrap the type calc in fix, and then you wrap each value in fix as well. And then, voila, you have infinite recursion. It's interesting that you can actually go back and forth between a calc of a fix and a fix of a calc. This is proof of that. You might want to look at it and convince yourself that it's really true. Anytime you have one or the other, you can easily jump back and forth, and it doesn't matter. So, to summarize, all you need to know is when you have something with hard-coded recursion, just introduce a new type and then wrap it in fix. All right, next, let's talk about algebras. This is the definition of an algebra or an F algebra. So for those who don't know Scala, this is creating a type alias. So it says that anytime I have an algebra with an F and an A, just turn that into this function on the right-hand side, which is an F of an A to an A. Now, because Scala, you can often do the same thing 50,000 different ways. These are all different ways you can represent a function from, what am I doing here? A list of an int to an int. So at the top, different ways of writing Scala, but they're all actually the same. You can take any of these and then just apply that type on the end, and it works. Scala understands that they're all the same. They're all algebras. Okay, so what? Well, there's a special function. I'm just going to call it awesome for now. If you give it a data, which is for any kind of f, as long as you have a functor, any kind of f, if you have a fix of that f, and then you have an algebra, which goes from an f to an a, then you can get an a back. So what? It didn't go to the slide. I thought it would. Algebra needs. Okay, please read. Algebra needs an FA, no A in fix, like magic. That's what happens when you don't look at slides for a few months. That's right. I was absolutely blown away the first time I saw this, by the way. Like, I thought, how could it possibly work? Have a look at the left-hand side. Fix of an F. There are no A's in that at all. But on the right-hand side, we've got an algebra. The input to that algebra is an F of an A. We don't have any A's on the left-hand side. How could this possibly work? If you just think about parametricity, it doesn't seem, to me, it didn't seem possible. It just seemed like magic. It is magic and it does work, but we'll get to that. Okay, let's try it out. I sort of skimmed over something before. I said you need a functor. This is a functor. So Scala Z has a notion of functor, cats has a notion of functors. It's basically a really simple abstraction, generally speaking, that says it has map on it. So a map from, so like if you have a list of A's, you can call dot map and you get a list of B's. This, if you're doing this yourself, this is just boilerplate. You can just copy and paste this without knowing what a functor is, and then just substitute calc into whatever your data type is. And then just where the 3 question marks are, if I expand that, you just satisfy it. You just make it compile and you're good. So back to our calc example, the top and the bottom are just that boilerplate from the previous slide. The middle is the implementation that's specific to calc. And as you can see, it's quite simple. Anytime you've got an A, you just wrap it in F. Simple as that. Okay, so now that we've created a functor, we can get that prerequisite out of the way and move on. Let's try a function that actually evaluates one of our calc instances. We do that like this. We define an algebra that says, given a calc, we're going to get an int back in the end. And then you just pattern match on it, and look at that, there's no recursion in that. What you're seeing, what these A's are and what these B's are ints, because the type here is a calc of ints. So everywhere you saw an A before, you're going to be ints. You're not going to have recursion. There's no recursion here. It's amazing. So you just add your ints together, you multiply your ints together, you return the one int that you have. It's trivial and awesome. Speaking of awesome, if we go back to that awesome function that I told you about, we now have everything we need to satisfy this. So we've got an eval function, which is the algebra. Let's just say, I'm not going to show you the definition of this yet. Let's just say we have a fix of calc. A fix of calc. We've got all we need. Now, if we call awesome with my imaginary C value and the eval function, it returns a 9 in this case. Why a 9? Well, let's ask it. I'm not going to tell you what definition I used. Let's get it to explain itself. So I'm going to create a new algebra now called explain. Instead of going from a calc to an int, this is going to go from a calc to a string. And it's just as trivial as before. In this case, take an int, turn it to a string, done. For these cases where you'd normally have recursion, they're already strings, like bloody magic, it's awesome. And then you just create a new string and do that. It's very straightforward. Now we could just run evaluate first and then run the explain function and then get the 2 values and say, oh cool, now I know what they both are. But because we were actually abstracting over our recursion here, we can actually compose these algebras so that instead of having to recurse through the whole tree twice, right, you just do it in one pass and do both things at once. So I don't think I show you the definition in these slides, but it's not complicated, and you can work it out yourself pretty much. But yeah, you can. It's quite trivial to zip 2 kinds of algebras together and get a new one. So here if you have a look at explain and eval, I've just called zip, and what I get on in the return type is a pair. The explanation on the left-hand side and the result on the right-hand side. So now let's pass this imaginary function to awesome, and then it returns. Oh damn! I've got to stop doing that. Then it returns this. See, explanation on the left and the value on the right. It's really cool. Okay, so the real name of awesome is catamorphism. I didn't want to lead with catamorphism because that tends to make people go and feel a bit overwhelmed if you're not used to this kind of stuff. But it's just a name. I think kata means down in Greek. So what this does is that it goes all the way down. I think that's the analogy here, to the bottom of the tree, and then calculates its way back up.
Actually, catastrophic morphism. So it's actually like a
really?
thing which completely explodes.
It collapses.
Collapses it down into.
So
it changes it down into its.
Right.
Destroys.
Well, yeah, because this is collapsing as well. It's collapsing a whole tree into a single value.
Collapses the structure into a value.
Yeah.
Right.
Anyfold is a catamorphism.
Yeah. Right, so there. Now everybody knows what a catamorphism is, and if you didn't know, anyway. So, how does it work? This is just because I find this interesting. It's not because it's essential. So I was saying that you could go back and forth between fix and something with a fix in it, right? This is ASCII category theory, by the way. Okay. Oh, I haven't looked at this in a while either. Okay. So let's just, I'm going to introduce an assumption, right? Let's assume that there is a means by which you can go from a fix of a calc to an arbitrary A. Let's just assume it's there. So I'm doing that in dashes, sorry. Well, if we had that, if this function existed, down the bottom, we could do this. We could say, well, we've got a calc with that inside. We can map, because we can just map on whatever's in calc. That's why we had the functor. And then we can just pass it that function that we assume exists. And then if you follow the types, what you get as a result of that is a calc of A. If you have a calc of A, well, we know how to turn a calc of A into an A. That's the algebra. That's the exact type of the algebra. So we just apply the algebra, and then we get to an A. Right, and then we just turn that into code. Assume the very first line is the assumption that we have a method called Carter that works. We don't know what the implementation would be at that point. But then we just take it, and then we just follow the arrows down that way, and that way, and we get there. And if you're looking for the recursion, you'll see that Carter appears there too. So this function actually references itself, which is fine. And then that's the trick. So not essential, but very, very interesting. Yeah, and then if you squash it into something a bit more concise, it looks like that. Oh, and in superior Haskell, it looks like that, which is, I think, much more readable. So you can separate it by dots. Like that goes first, then that goes first, and that goes first, and that's exactly what you have. You go there, you go there, you go there. So I find that quite readable. But yeah, you don't need to know. It's just interesting. So all you need to know is create a functor, create an algebra whenever you want to reduce a tree, and then call Carter, and then that's it. That's really cool. So now we're going to talk about coalgebras. Coalgebras are the dual of algebras. What do I mean by dual? Well, in category theory, everything can go backwards. Flip all the arrows around, and everywhere you've got a construct, turn that into a dual as well. And all the laws of gravity and Earth and whatnot hold. So our FA to an A, flip everything around. It's actually an A to an FA now. So whereas with an algebra, you would squash an F into a single A, with a coalgebra, you start with an A and blow it up into an F. Yeah, and using different terminology, you would say in the first case, you fold something into a single value. The other case, you unfold it, potentially infinitely. Okay, so here we're going to do what we did before. We'll create a coalgebra type alias. A coalgebra of an F and an A is an A to an FA. And this is an example implementation. Given an int, like a sort of seed int, return an expression that breaks it into factors. So we just keep multiplying things by 2, and then when we can't do that anymore, we just return the remaining number. So we have another magic function. We had awesome before. Now we've got awesome backwards. Emo siwa. So just as everything else was flipped, this function's flipped as well. Data is now an A, so the A is not on the outside, the A is on the inside now, and the fix of an F is on the outside. The algebra is now a coalgebra. And notice that there's no A in the result anymore. It's just in the input. So this is called an anamorphism. It's like I said, it's the opposite of a catamorphism. If I show you them both in a special way, I think you can see that they actually are, one is the other backwards. Yeah, and this starts the root and calculates its way all the way down to the nodes until it decides to stop. So if you want to use this, all you need to know is create a coalgebra whenever you want to build some kind of recursive structure. The input you can consider the seed or an instruction or a specification. and then call the anamorphism, and you're done. That's all there is to it. Okay, so these are the basics of recursion schemes. We've covered fixed points algebra, coalgebras, catamorphisms, anamorphisms. There are lots of other stuff, but I think they mostly build on that. There's a library called, I'll talk a bit more about Matroshka later, but these are some examples. This is taken from Matroshka. These are some examples of other kinds of structures. So we've covered algebra and coalgebra in the middle there. There are many other kinds of algebras. And the same thing with morphisms. There are a lot of morphisms. Here we've only covered kata and ana, but there's a whole mountain of them. Right, before we get to the live demo, there are two extensions that I find super useful if you're doing FP and you want to start using this stuff. A lot of the time, you'll find that the algebras and coalgebras that you write, you want to put, oh, wait a minute. Oh, jumping ahead of myself. Okay, sorry, the first thing here is operator fusion. In the same way, if you have a list, if you go map F and then you go map G, that's instead of iterating over the list, creating a new list, and iterating over again, creating a new one, you can actually just fuse those, the F and G together and compose them and have one function, call that once, and then you end up only traversing the list once. The same thing here. You can actually combine a catamorphism and an anamorphism into a single operation, which is a hylomorphism. This is very, very cool. So it's the same. It's actually the same as just calling ana and kata. It's just more efficient. Right. So this is the type. This is the what is it? Type signature down the bottom. It takes a coalgebra. It takes an coalgebra of an F and A, meaning it's going to build something up based on an A. Then it takes an algebra that says, given an F, I'm going to spit out a B, and then all you have. And then you just give it the initial A, and you get a B out. It doesn't create a whole structure. It doesn't, and then traverse the whole thing. It just does it inline, which is really, really, really cool. Another way of looking at this: once unfold, once fold. You call it an unfold into a fold. So, yep, like I said, builds it up and tears down the whole thing in one pass. Doesn't create a whole tree first. So it'd be big theta n instead of 2n. Right, this is what I was getting at before. Monadic versions. A lot of the time when you're creating these functions to sort of squash a tree into a value or create a tree, you want to do it in some kind, you want to have some kind of effect, some kind of monad there, so that you can control, I guess, account, words elude me. Yes. If you want to do things like, say for example, if you want to do the whole thing asynchronously, well, everything's going to start returning a future from now on. So that's an example where you can't just, you have to compose those futures together monadically as you go, as the kata or anamorphism goes through the tree. So there are monadic versions of these. Oh God, yeah, right. What's a monad? Not everyone knows what a monad is. Okay. Extremely loosely speaking, it's a wrapper around some kind of data or intent to do something that you can keep composing. You can also think of it as something that has both map and flat map, and you can put it in a for comprehension. So I'm sure most people have used monads already. Here are some of the most common options, lists, futures. If you ever have a for comprehension and compose these things line by line, that's monadic composition. Okay, so going back to our evaluation thing, going back to our evaluation function, let's make it error out if there's a division by 0. Let's just say we introduce division. If you haven't seen these, what this funny little symbol is, it's from, I did it again. It's from logic, it's a disjunction. I'll just skip this. Okay, so here we're saying that we can return either a string or an integer. If it's a string, that means it's an error. If it's an integer, that means everything was okay. Keep going. So we'll put correct values on the right-hand side, so they're always integers. And if there's anything goes wrong, we'll put on the left. That's a string. And we we expect computation to stop. Once you hit an error, it just stops, and then that's the final result. It's an error. So whereas we had algebra and coalgebra up the top, F808A, 808A, now if we just introduce an M for the monad, the M goes on the right-hand side. So they both return monads. So it's an FA to an MA and an A to an MFA. So again, how we had unfolds and fold before, non-monadic. The monadic versions are very similar. We just take an M, which is a monad. We change the algebras and coalgebras to take M's as well. The result is now wrapped in an M. And there's one other difference. Right, I'm writing the same thing down here. Okay, there's one other difference, which is before I said you need a functor. It's just a prerequisite. Well, now the prerequisite for monads is you need a traversal instance. I'll show you what a traversal is later. Okay, so back to that other example where we were monadically handling errors. Saying if something goes wrong, we're going to put it on the left-hand side of our type, which is our string or an int. If we define a type A this, saying it's a string or an A, so that's what that is there. That fits this string or now fits the pattern. The string or is the M. So we can say we're going to have an algebra which operates in a string or context, takes a calc, and if everything's okay, returns an int. So it might take a little bit of time to wrap your head around this if you're not used to it, but with just these tiny little changes, we've added error handling and short circuiting. And that's not something that's hard coded here. That's you when you define your own monad. Here I'm using the disjunction, which is where you get the short circuiting, but you can define your own monads to do whatever you want. So, okay, demo. I'm going to write a random JSON generator that shows everything that we've covered. Okay, so generating random data is quite important. Whenever you do property testing, you want to have random data because that way you theoretically will cover all possible cases of data that your code can handle. It's the secret sauce of property testing. It's useful for load testing as well, stress testing, benchmarking. If your generator is deterministic. Okay, so there's a library that I've written called Nyai, and don't ask. And I'm just going to give you one of the things it does is random data generation, and I actually think it's the best in Scala land. Not very humble to say that, but I think it is. In terms of random data generation. So I'm going to give, this is an example. Say we've got some class called whatever. This is just part of our normal code, and it's got a boolean, 2 ints, and then a map of a long to a this to a that. If we wanted to generate random instances of these and use them in our tests or load testing or whatever, this is how you would do it with Nyai. Just import it, crap. And then we use this gen class. Gen is for generate. So then we put it in a for comprehension, and it's just field by field. So enabled, generate a boolean, position, we're gonna customize that a bit. We'll say it's between -128 and that, turn it into a pair, blah, blah, blah. So, and look at that map, gen.long map to, I like it.
Just one question.
Yes?
Is that going to put the position along the diagonal?
No. For each int in that pair, it'll generate a new value.
It generates a new value, so that's
Yeah.
a generator. That's a pair of generators, not a pair of ints. Then
It's a generator that generates a pair of ints, and each int will be generated differently.
Okay.
Also, like regenerated, if you know what I mean, yeah. So this is a sample. So if you call dot sample, which is part of the gen framework, this is an example of something that you could get out of this. So with that small amount of code and a somewhat complicated type, it's quite trivial to generate random stuff. So I'm introducing that because I'm going to be using that in the demo. Hint, gen is a monad. We're using it in a for comprehension. It's got flat map, it's got map. That's enough for us to call it a monad for our purposes. It's a real monad as well. So our imaginary app uses play.json. Play.json has hard-coded recursion, so we can't use any of our cool tricks that we've learned. We can't make anything efficient. Instead, we're going to create our own JSON type. So I'm just going to call it JSON F. Now this follows the pattern that I've described before. So we're going to create the base type, and then this A here that I've got is going to represent recursion. So nulls, booleans, strings, numbers, none of those actually use the A. We're declaring them, they go to the end, and then they don't get used. See, boolean, string, double. They get used here. Arrays have a list of A's. Objects have a list of fields, which are strings to A's, which will usually be the recursive JSON, keep in mind. Let's clean this up a little bit. We'll use covariance to simplify that. This just makes it look a bit nicer. I won't get into that. Okay, now traverse. We talked about, I gave you the sort of skeleton for functor. This is the skeleton for traverse. If you don't know how to use this stuff, no worries. Copy and paste this, and then just there you go, change JSONF to whatever your data type is. And then you'll have to fill in the question marks. How do we do that? This is what we do for our case. If you don't know how this stuff works, I can just give you some basic, really simple rules. It's not the point of this talk how it works, but depending on how many A's there are in your type, just use one of these. If there are no A's, just use g.pure. Oh, I'll show you where g comes from, by the way. G is provided to you by the function. So the function will give you a g. So if you've got no instances of that type, just call g.pure. If you've got one, call apply to, 3, apply 3. If it's a list or something else like that, just call .traverse. Yeah, this case here is a little bit nasty, but if you think about it, it's not that bad. Anyway, it's a one-time pain, and it's good learning. All right. So I omitted those two from the demo just to save time, right? There are only 4 things we need to do to get this demo to happen. We've done the first 2 just on screen to save time. Create a data type, create a traverse instance, which also gives you a functor, by the way. Now we're just going to generate, we need a generator for the JSON that turns it into our custom type, and then we're going to turn that into play JSON. Live demo time. Okay, so I've got this class, there's not much in it. This is the definition of our JSON type, and this is that traverse instance that I told you about. It's the same as the slides. I've got a main function here that soon I'm going to enable. I'm going to comment this out and make use of a generator, take some samples, take 20 samples, print them on the screen. And that's all I've got at the moment. Like, there's nothing else here. Right. So I've created this in advance as well, because when I generate strings, this is what I want to use to generate strings. I'm just saying alphanumeric characters and 0 to 10. I don't want to have huge strings for the demo. Right, so first thing we should do is the goal. Oh wow, coding in front of people is hard.
Just thinking, can you make the text bigger? I mean, I can read it, but I couldn't read it.
It might be a little bit of a... Oh no, I'm already there. Boom. Did anything happen? Huh? Sorry? Because of reasons, I don't want to use that. I'll just make the text bigger. We can do it. Bigger?
36.
How about I just go up by little increments? Really? Okay. How's that?
Yeah.
Yeah? Good? Okay. Is that better?
Yeah.
All right, cool. Yeah, I know. Sorry for the wasted real estate here. Right, so I'm going to start by defining the goal. The goal is I want to have a generator. So let's have a generator. Oh God, coding in front of people is not easy. All right, it's going to be a gen. I don't care about the body. And the gen is going to be a JS value, which is a play data type. And that should be enough for me to comment that out. Oh, I'm going to put this in the background, by the way. Ah, no. So we'll have compilation over there. So that compiles. All right. Next thing, there were 2 steps to doing this. One is we're going to generate JSON in our custom type. So let's have a generate JSON. So that's going to be a Coalgebra because we want to create it. Coalgebra in the gen monad, and we want to create JSON. Now this is an interesting one. This is the A. This is that seed value that I was talking about. I'm going to just put this to unit at the moment. All right. Next thing. JSON to play JSON. And how do we do this? This is going to be an algebra because we're taking a tree and we're going to turn it into something else. So we're going to take this kind of JSON and then we're going to turn it into play JSON. Okay. Now, assuming those 2 are implemented, I'm gonna fill this out. I've got this little helper here, easy recursion. So we want, it's going to be monadic. We're going to do that monadic fold into unfold that we're talking about. So comonad first, that second. I'll show you the type signature, by the way. Blah, blah, blah. So takes a coalgebra, takes an algebra, M, takes an A. Sorry? All right, and then we're going to take some kind of A here. Now this is an algebra, not an algebra M, but that's okay. I've got something prepared for that. It's easy to take anything that's not in a monadic context and lift it up into it. It's really easy. I've got a little helper method here, and it just does that. All right, now what do we need here? Let's do this. Put 1, 2, 3. It should complain and tell us what it wants. It's not complaining. Oh, okay, it's Scala. All right, discarded non-unit value. The point is it's a unit, just because we used unit there. Okay, that compiles. Now let's start filling this out. This is easy. This is just going to be a pattern match. So, oh, look at that. I've prepared something. Amazing. It's almost like I knew I was coming today. Okay. So, easy cases. So on the right are all going to be in the play types. They're not going to be in our custom types. JS boolean of value. JS number, I guess.
String.
Oh, thank you. Did someone just say duh? It's okay, I approve. I don't mind that. Duh, DK. Okay, now we're getting to somewhere interesting. So, if I inspect the type, look at this. It's a list of, you can say, it's a list of JS values. It's already in the play world. We don't have to worry about recursion. It's amazing. So I'm just going to call the play JS array and give it what I've got. That's it. Simple as that. I think it's going to be the same thing with the object. If I inspect that, there you go. List of strings to JS values. It's already been converted like magic to play stuff. All right, hit save. That compiles in the background. Beautiful. Okay, now this is a bit more interesting. I'm going to say, what? It's a function. So what's that? Unit. That makes sense because it's an A to an MFA. So let's just ignore that. Now I'm going to do this. Now there's no problem with variables in, as long as they're not exposed, by the way. So I'm going to have an empty list of, well actually before I do that, let's see what we want back. So we need a gen of JSON F of unit. Okay. Let's just confirm that we want to have a gen of that of unit. I've just copied that from the command line. Look at that, works. Okay, cool. Let's start doing this for real. No. Okay, and now what we're going to do is just for each case, I'm just going to add a generator for it. So gen pure JS null. I mean, I know how my library works. I'm not going to explain that, but gen, we get a boolean, see, boolean of gen, and then we're just going to map that boolean into playland. Same thing with strings. Map it into a string. It's starting to feel very boilerplatey at this point in time. It's not. I'm not thinking very much. I'm just satisfying types. Generate a double. Map it to a number. See if the compiler is going to catch me if I do anything wrong. Now we're going to get. Now these cases are a bit more interesting.
David, can you just quickly explain colon equals?
All right. So colon equals. This is sugar for. For this. Oh, what am I doing? No. Okay. So colon equals is the. Okay, is this just IntelliJ being IntelliJ or what? What am I doing? Okay, I don't know why that's not working. But anyway, that's what it does. It's assignment. It's saying sorry? Sorry, type inference. Oh wait, what am I? Oh no! My bad. Okay. Sorry, this is my mistake. Look at the type signatures. This is a coalgebra. I'm supposed to be generating JSON Fs in my custom type. What I've been doing is generating play stuff, which doesn't make sense. So this is what I was missing. JSON. Yes, they catch all these things. So here we go. I'll generate JSON F versions. Boolean. This is string. This is number. Bet you Python people are jealous now, huh? All right. What? Trying to do this without actually thinking. Oh, thank you. Anonymous hero. Okay, finally, thank you. All right. All right. Now we have compilation. Now, now this case is a bit more interesting. This is what we want to generate, right? JSON F of unit. If we go back and have a look at the array case, that means we actually want, well, the A is going to be unit, which means we want a list of units. Okay, let's just satisfy compilation, not think about it. So I'm going to go gen.unit, and I'm going to say list. I'm going to map that into JSON F array. I think in this case I have to put that there. And happy days, it compiles. Actually, I might just restrict this to 4. Okay, now we'll do a similar thing for objects. What is it? It's string. So this time it's going to be a string to unit as a list. So let's take that gen string, map it so that it's string on the left and unit on the right. Create a list of them, say 0 to 4, map it. Oh God, we're running out of space. JSON F object. All right, and now let's squash all of these. This has an exclamation mark because there's no type safe proof that gen is empty. There's a different method that accepts proof of that, but it doesn't matter. And that compiles. We've covered all cases. And to be clear, these are the non-recursive cases. Recursive cases. Okay, so that all compiles. I don't think we have any other triple question marks anymore. let's actually run this. Cool. All right. Now, pretty no. As if this talk isn't going long enough. Okay, that's not interesting enough for me because look at this. We haven't really. Oh, where the hell am I? This is huge. Oh God. Look at this unit. We haven't really made any use of this. Of the A in the coalgebra, and for a while I struggled to find a decent or use case of when you would populate that. So let's make use of this. I said it can be a seed value, a specification, or something else. We're going to use a specification. So what I'm going to do is I'm going to create a case class called spec, and I'm going to say we're going to control how we generate this value. So I'm going to say it's got a minimum depth, it's got a maximum depth. And we're going to feed that to the algebra. So I'll change that there. This type, if I inspect it, it's now a spec. So I'll change that to I'll just call that spec. Now, down here we get a compile error because we had unit before. Now it needs an actual spec. So let's do let's do this. Let's give it a specification. Okay, this is what we want our new world to look like. The reason I didn't just pass in a spec up here is because there's one important detail missing. In order for this coalgebra to understand minimum and maximum depth, it needs to know its current depth, or else what's it going to do? So, excuse me. I'm going to put current depth in here. And then I'm going to set it to 1 when we call this generator function. Now, oh, this is huge. Where am I? Okay. Yeah, temporarily. I'm also going to just define some helper methods quickly. Has the min depth reached, I guess? Reached. Oh, yeah. Okay. Has the minimum depth been reached? Well, it has if the current depth is greater than or equal to the minimum depth. Similarly, the maximum depth has been reached if that exceeds or is equal to the max. Sorry? Oh, it's just IntelliJ. Okay, now to make use of it here. Well, it might take a little bit of thought, but if you think about it, it's quite simple. All we have to do is say, well, has the minimum depth been reached? If so, these non-recursive, i.e. terminal, cases are allowed. No. Because the idea here is that if you haven't reached the minimum depth, you want to force recursion. You want to keep it going. Down here, we say, has this, it's a bit different. If we haven't reached the maximum depth, then keep recursing. We'll allow further recursion. Now remember how we just put, okay, first of all, this should not compile. Good, it doesn't. Now this is correct because before we were passing in, for that A, we were passing in units. See, unit. Now we need to change that to a spec. So it wouldn't make sense to pass in the same spec. That means it would just be looping forever. Let's update the specification for the next level of recursion. So I'm going to say next level is the spec. Make a copy of the spec. Space. And then just say the current depth is equal to, well, the current depth just increases. Does that fit in one line? Yeah, fits enough. So then we just put that there, next level. This is a pure value, just reuse it all over the place. Have I erred? No, that's fine, that's fine. Okay, so all that works. Cool. There is actually one problem with this, which isn't immediately obvious, which is this 0. I mean, if you're going to force recursion, you can't stop at 0 because then it won't recurse. So, so I'm going to say the minimum size. Oh, I can't remember what this one is. Cheat sheet, cheat sheet. Okay, there we go. Save typing as well. Okay, so this is what we do. So if we've already reached the minimum depth, then we can stop recursing. So a minimum size of 0 is fine. We can have an empty list, no problem. Else, just force at least one nested value. Change that to that. There you go, minimum size of 4, minimum size of 4. Done. Now, all we need to do is make use of it. Well, I'm going to create another function just quickly. I'm just going to say generate exact depth. Depth of 1. And all this is going to do is just create a generator that has the minimum and maximum set to the same number. All right, so before I do that, let's just run it in the background. Let's change that. Actually, I'll put that on 10 as well. So let's start at depth 1. There you go. Look, no recursion at all. Let's just take more values just to be sure. None of those are recursive. They're all flat. If we want exactly 2, there you go. Everything has exactly 2 levels of recursion. Cool. All right, that ends the demo. So, I mean, to wrap that up, that's an example of something that you would feed into a coalgebra. You could tell it exactly how to generate what it's going to generate, which is pretty cool. Right. All right, so that's the bulk of the talk. In summary, recursive data types. These are some examples of them. Trees, indent, because this is where you can apply this stuff. Everything that you've seen so far, these are great ideas of application. You can put them in trees, indented lists, prefix trees, DSLs, expression languages, anything self-referential, logical propositions, assertions, composable action, and composable data. It allows you not to think about recursion. I didn't think about recursion very much at all in all of my algebras and coalgebras, mostly. I just went blah. It was the very simple case. It's like magic. I think traditionally there's been sort of a high barrier to entry with this kind of stuff. I hope that I've demonstrated this in a way that people who haven't maybe been introduced to the academic side of this or seen functional programming as much get it. I don't know. But look, in the same vein, like I don't know how cars work. I can drive them. It's the same thing here. You don't need to know how this stuff works. Just remember how to do what you want, and then you can get what you want out of it, and learn the rest later. Right, so those little functions that I talked about. Okay, look, basically, get access to those functions like catamorphism, anamorphism, fix. They're from a library, or copy paste it yourself because they're really small. Parameterize your data, use fix. And then just keep writing functions like you always do. Just make sure they're in the right shapes. Just make sure they fit the algebra or coalgebra shapes, and then that's it. Libraries, I've got my own tiny little library. It's a micro library. Then that's what I was using just now. It's got the basics of recursion, which is what I showed you today, and maybe 1 or 2 more things. It's fast. There's like I said, there's an object called easy recursion. So if you're trying to introduce it to a team where not everyone has the time to go learn this could be a good way of doing it. Everything's in English instead of Greek. Hopefully that works. Otherwise, there's a library called Matroshka. It's very, very comprehensive. It's got everything in the world to do with recursion. It's really covering the whole spectrum here. It's going to be part of the type level suite. Lots of smart people are working on it. Check it out. It's cool. If I didn't make sense to you today or you want more information, check out these resources. This is what helped me learn all this stuff in the first place, and I think it's, especially the talks by Greg, I think they were absolutely awesome. I'll wait until all the cameras go down. Which means I didn't make sense to anyone. That's cool. Just go here. I'm just evidence that people can learn. That's fine. I'll send out slides as well. Okay, cool. And thank you everyone for enduring this. And thanks for these two guys for helping me. Okay, any questions?
Thank you for a very nice talk. That was very interesting.
Thank you.
I had a question about hylomorphisms.
Yes.
So in Haskell, they are more efficient, but don't rely crucially on the laziness, because you need to expand one level and then on demand expand it and then reduce it with the catamorphism and then the next layer and the next layer. Do you need, in Scala, do you
need non-strictness? No, I'm not sure that the efficiency does come from non-strictness in that case. I mean, like, I'm not an expert on this, but I believe it's the algorithm itself that gives it to it, because I don't know, I can't see where laziness would benefit. It, like everything in that tree, yeah.
Sharing the tree, so
yeah, nothing gets skipped. Everything gets evaluated.
You generate everything and then you have to tear it down again. Talk about deforestation.
But I think the efficiency here comes from fusing it into one pass, so that you still go through an entire intermediate tree that never really exists in full, I don't think, in memory. But you do visit. You still end up visiting all the nodes. Everything in the tree gets visited. Yeah, I think that's as much as I have on that.
Composition, where you get problems, which is also
composition
to the problem of the fact that your recursion is not Taylor recursive. So there's not even a simple Taylor recursion that Scala can do. So have you had problems with essentially
stack overflows? Well, first of all, I've got that horrible, annoying answer that everyone defaults to, which is it supports monads. You can use a trampoline monad. I'm sorry. Is there a better way? Does it? I've got to think of the. No, I think it would be prone to stack overflows. Actually, it would actually depend on the functors and traversals. I think that's where the recursion is happening. Yeah.
Well, the recursion actually is not recursive, so
no.
It will simply, even if you have a trampoline in there, it'll still expand stack.
Oh no, I think you should be safer with a trampoline though, because the recursions, it's deferred to the monad itself, and the contents there are non-strict.
Which is not necessarily a terrible thing. It depends on the depth of your recursion anyway.
Yeah.
And most recursion schemes don't necessarily go that deep. But
yeah, I
would see any of those problems.
No, not me. It'd be interesting to talk to the people who work with Matroshka, because they're using this like all the time, a lot. Yeah, sorry, I haven't encountered that kind of stuff. Yeah. Hey.
Just a dumb question. So why, at school you get confused by algebra? Why is that thing called algebra?
Oh, I meant to look this thing up actually. This is an F algebra, I think, formally. Or it's an F, yeah, it's an F algebra. And I know they use algebras to me, like even ADTs they refer to as algebras, right? I don't know. I don't remember the guy's name. I don't remember his face. Someone's got a blog post on that, and I meant to read it, but I've been busy with other stuff, so I do not know. If anyone else does, I'd love to hear the answer to that as well.
So an algebra is basically a closed set of things, and so it could be A, B, C, and D. form an algebra, which is the thing of A, B, C, and D. That's really all that an algebra means. It's just a closed set of things. So, they talk about the algebra. Calc is formed of add, multiply, and a number. Right, that's it. So algebra is one of those words that sounds scary, but it really just means a closed set of things. So,
Yeah. And I think in this case, where I'm talking about algebras to represent functions from FA to an A, I think that's different. I mean, that's a different case. It's not the same kind of algebra. And that's what I was saying. I think that's what F algebras refer to.
I thought it was the closed set of things and the defined operators on that set as well.
but I mean, the closed set there is the number of things which create the function FA to A. And so there is a bunch of things that define that thing. And they are, in the case of your...
maybe F is functor or function or something.
So
you've got the set of A's and the operators multiply and add. That's it.
They chose a word because you plug in certain values, you have to get out things that are known to be algebras. So, yeah, usually this kind of pattern in maths is called a module, but for this reason, because the module means you've got something acting on something else. That's the function. Because they look like things like rings and whatever. Just right choices for F. That's why they chose the word.
Right.
Hey, David, that was pretty mind-blowing. Especially the really simple bits that do a lot.
Good.
But can you say anything at all about how this fits into the larger world of data and co-data? Can I chuck out my transducers and deducers? Can I throw on my iterators and use? I'm not asking you a specific question, but do you have any remarks?
I may not have a specific answer either, or even a specific response. I don't know.
Too general, a question?
It may be a little bit for me right now, with
is
lights
it
on my face. Yeah,
like-
sorry.
Is it like other things you've used, like iteratees or something, and you
No,
now
not at all.
You now use a...
No. This is the first time I've ever really seen recursion abstracted over and abstracted in such a way that you can actually start manipulating the details of recursion separately than the logic that you want to use in conjunction with the recursion. Because normally those two always get smashed together because the data is recursive.
Yeah,
And I've never...
Impossible to pull them apart until you know the truth.
Yeah, exactly. So for all those cases now, I look at it with these eyes and think, wow, it's this would be much
just
cleaner.
Exploration there, but I like it. I like what you're saying.
Yeah, thanks.
Are your slides and the code online anywhere?
So, are they what, sorry? Online?
Online?
They will be, yeah. They're not at the moment.
and you'll post them to the Scala seed.
Absolutely.
Yeah. Wow.
Yeah, we'll do.
Right. More. Right. Thank you, David.
Cool.
That was awesome.
Thank you, everyone.
Right. So